comprehensive guide to Hadoop YARN ApplicationMaster. Architecture, functionality, and implementation. This presentation will provide an in-depth exploration of the ApplicationMaster, a core component of the Hadoop YARN framework responsible for managing application lifecycles within a cluster. The ApplicationMaster, often abbreviated as AM, is a core component of the YARN architecture. It is responsible for managing resource negotiation with the cluster, scheduling an application's individual tasks, and monitoring their execution. Unlike HDFS components like the name node or data node, which manage storage, the ApplicationMaster operates at the cluster resource management level. It is the fundamental reason why YARN can support diverse frameworks like MapReduce, Apache Spark, and custom applications. In this session, we will explore the ApplicationMaster's architecture, its complete lifecycle, and how to implement one for your own needs. To understand the ApplicationMaster, we must first understand why it was created. Hadoop 1.0 had significant limitations. It relied on a monolithic component called the job tracker, which was responsible for both cluster resource management and job execution monitoring. This created a single point of failure and severely limited scalability, capping clusters at around 4,000 nodes and 40,000 concurrent tasks. YARN, which stands for Yet Another Resource Negotiator, was introduced in Hadoop 2.0 to solve these problems. Its key innovation was the separation of resource management from application execution. This separation enabled multi-application support, moving far beyond just MapReduce. YARN's architecture is built on three core components. First, the ResourceManager, or RM. This is the central authority that governs all resources in the cluster. It consists of two parts, the scheduler, which allocates resources to running applications, and the Applications Manager, which manages the lifecycle of every application. Second, the NodeManager, or NM. This agent runs on every single machine in the cluster. Its job is to manage containers on its node and monitor the usage of resources like CPU, memory, disk, and network. And third, the ApplicationMaster, or AM. This is a dedicated per application controller. Each application has its own instance of an ApplicationMaster, which negotiates resources from the RM, schedules its tasks, and monitors their progress until completion. YARN operates on an elegant two-level scheduling model. Level 1 is global resource management, handled solely by the Resource Manager, which tracks all available resources and makes high-level allocation decisions. Level 2 is application-specific scheduling, where each ApplicationMaster is responsible for requesting the resources it needs and then scheduling its own tasks within those allocated resources. The key architectural components involved are the Resource Manager, the node managers on each node, the various ApplicationMasters, and the containers themselves, which are the isolated execution units where tasks ultimately run. Let's walk through the life of a YARN application step by step. 1. A client submits an application to the Resource Manager. 2. The RN's Applications Manager allocates the very first container, specifically to host the ApplicationMaster for this application. 3. The newly launched ApplicationMaster registers itself with the Resource Manager. 4. The M begins negotiating for resources, requesting additional containers from the RM to run the application's actual tasks. 5. Once containers are allocated, the M works with the node managers to launch the containers on the respective nodes. 6. Throughout execution, the NM constantly monitors the progress of its tasks and reports back to the RM and the client. 7. Finally, upon completion, the M signals this to the Resource Manager and cleans up all of its resources. The ApplicationMaster has 4 primary responsibilities. First, resource negotiation. It communicates with the RM to request containers that meet its specific requirements. Second, task scheduling. It decides which task to run in which container, often making sophisticated decisions based on data locality. Third, progress monitoring. It tracks the status of all its tasks, handling successes and failures, and reports this status. And fourth, fault tolerance. It is responsible for handling failures, such as by requesting new containers to retry failed tasks. Its lifecycle follows a logical sequence, from initialization and registration, to resource requests and container launch, through continuous heartbeats, and finally, cleanup. Internally, an ApplicationMaster is built using specific clients for communication. The MRM client async is used for asynchronous communication with the Resource Manager. The NM client async is used for communicating with the node managers. These clients use callback handlers to process incoming events from the RM and NMS. This communication is governed by formal protocols. The Application Client Protocol defines communication between a client and the RM. The ApplicationMaster protocol governs talks between the AM and the RM. And the Container Management Protocol is used for communication between an AM and a NodeManager. The ApplicationMaster's lifecycle is a detailed process. During initialization, it passes command line arguments, establishes a connection to the ResourceManager, and sets up its internal services. It then moves to the resource request phase, where it defines its requirements for containers such as memory, CPU cores, and data locality. Once resources are granted, it enters the container launch phase, where it prepares the launch context, setting the environment, the command to execute, and any necessary resources like security tokens or job files. Throughout the run, it is in a constant state of progress monitoring, tracking task execution, and handling any failures. Finally, upon completion, it reports the final status to the RM, releases all its containers, and gracefully deregisters itself. Implementing a custom application master involves a series of clear steps. You begin by setting up a YARN client object, which is your connection to the ResourceManager. Next, you define an application submission context, which describes the application you are submitting, including the command to start your custom IM. Then, you must create a container launch context for your application master's own container, specifying its environment and launch command. Within the IM code itself, you manage resource requests, environment setup, and security. A typical implementation includes core methods like init for setup, run for the main processing loop, and cleanup for termination. Data locality is a critical performance concept for the application master. Its importance cannot be overstated. By scheduling computation on the same node where the data resides, or at least on the same rack, we minimize network data transfer, which dramatically improves application performance. Key strategies include making locality-aware container requests, specifying preferred hosts or racks. Delay scheduling, where the M waits a short time for a local container to become available rather than immediately taking a non-local one. And speculative execution, which launches duplicate tasks on other nodes if a task is running slower than expected. A practical example is an AM for a map-reduced job specifically requesting containers on nodes that hold the HDFS data blocks it needs to process. YARN is designed for fault tolerance, and the application master is a key part of this. Several mechanisms ensure robustness. Heartbeat monitoring between the AM, RM, and NMS detects if a component has failed. The AM can retry failed containers a specified number of times. For long-running applications, the AM can periodically checkpoint its state to persistent storage to enable recovery. High availability features include application attempts, where the RM can restart a failed AM on a different node. RM Restart Recovery allows a new resource manager to recover the state of previous applications. Failure scenarios are handled gracefully, and M failure triggers a restart, and NM failure prompts the M to request new containers from the RM, and a resource manager failure is handled by a standby RM taking over. To maximize cluster efficiency, we can optimize the application master's behavior. Resource optimization techniques include container reuse, where an M keeps a container alive to run multiple tasks sequentially, reducing overhead. Dynamic resource allocation, where an M can request more containers or release unneeded ones based on current load. And promptly releasing unused containers back to the cluster. Scheduling optimizations include uberization, where the AM runs all tasks within its own container for very small jobs, avoiding scheduling overhead. Priority scheduling and preemptive scheduling, managed by the RM scheduler. Finally, comprehensive monitoring through progress tracking, metrics collection, and log aggregation is essential for identifying performance bottlenecks. It's useful to compare the application master model to other frameworks. Compared to the old Hadoop 1.0 job tracker, the M model wins on scalability, flexibility, and fault tolerance due to its distributed nature. Compared to a Spark standalone cluster manager, YARN's application master framework is more general purpose. It can run Spark, MapReduce, and other applications simultaneously on the same cluster, while Spark standalone is limited to Spark applications. The comparison with Kubernetes is fascinating. They are similar in their core concept of container orchestration. However, YARN is deeply optimized for the Hadoop ecosystem and batch processing, while Kubernetes is a general-purpose platform designed for deploying a vast array of containerized applications, often with a focus on long-running services. When working with application masters, adhere to these best practices. For development, accurately estimate resource needs to avoid starving your application or wasting cluster resources. Implement effective logging within your M for debugging, and always code for graceful shutdown. For operations, set up robust monitoring and alerting for your applications. Understand and properly configure resource queue management in the RM scheduler, and always be mindful of version compatibility between your application, ISN, and the YARN cluster version. For security, ensure proper authentication and authorization are configured, and take care to protect sensitive data such as security tokens within your application code. In conclusion, the YARN ApplicationMaster is a scalable, flexible, and fault-tolerant component that is the key to multi-tenancy and efficient resource utilization in the modern Hadoop ecosystem. It supports a wide variety of applications beyond MapReduce. Looking forward, the evolution of YARN involves deeper cloud-native integration, potentially with Kubernetes, continued improvements in scheduling algorithms for better bin packing and fairness, and tools to simplify the development of custom application masters. Our recommendations are to invest in building YARN expertise within your team, carefully evaluate your framework needs to choose the right resource manager, and stay current with the rapid evolution of the big data ecosystem. Thank you.